All right, in this video we're going to take a look at arithmetic operations with vectors as well as solving vector equations. We'll take a look at some vector operation and scalar operation properties as well. So the component form of vectors allows us to justify some of the following properties for two vectors v and w. One of the things that I want to mention before I forget is the component form here allows you to kind of reset the vector so that way it has an initial point at the origin and its terminal point are the coordinates of whatever x and y are going to be. So we can move vectors around in the coordinate plane as long as we don't change their length and we don't change the direction they're pointing. So we could physically pick a vector up and place it so its initial point is at the origin and its terminal point will be whatever the components are here. So first we have vector addition, which is just adding your horizontal components and adding your vertical components. Sort of like combining like terms, combine your x's, combine your y's, or at least your x coordinates and y coordinates. Vector subtraction, same thing, but we subtract. We have the order in which we add vectors does not matter, so vector v plus vector w gives you the same result as vector w plus vector v. By the way, the result that you get from adding two vectors together is called the resultant vector. And because the order of vector addition doesn't matter, we say that vector addition follows the commutative property. So order in which you add is not important. We have the associative property where we take vector u plus vector v, figure out what that sum is, and then add vector w to it. It's going to give us the exact same answer as adding first vectors v and w, and then adding vector u, to that sum. So this is the associative property where we can shift the ones that we add together first, and it won't change anything. The identity property says if we add the zero vector, which is just 0, 0 in two dimensions, to a vector, we get the original vector. So it's a little bit of a follow-up on this one where w1 and w2 would both be 0. So it's called the identity property. We have the inverse property that says if we take a vector and add its inverse, which we just make the components the opposite of what they are, if we add those together, we'll get our zero vector. So it'd actually be a zero vector, not just 0, but that's the inverse property. So example 2, let vector v equals 3, 4, and suppose vector w, has an initial point p at negative 3, 7, and a terminal point q at negative 2, 5. We're going to find the resultant vector v plus w and interpret the result geometrically. So first, let's write w in its component form by taking our terminal point, negative 2, the x-coordinate, and subtracting negative 3 for the initial x-coordinate, 5 minus 7 for the y-coordinates, and negative 2 minus negative 3 is 1, and 5 minus 7 is negative 2. So from p to q, we'd have to go one space to the right and two spaces down. So now that we have vector w in its component form, vector v plus vector w, we take the 3 plus 1 for the x or the horizontal components, and then 4 plus negative 2 for the y or the vertical components, and we end up with 4, 2. So let's take a look at what this means from a visual perspective. So here's vector v, went over 3 and up 4. Vector w, remember, we can put vector w at the origin if we want, once we know its component form. But the component form for w was 1, negative 2, so if we have vector v at 3, 4, vector w is going to begin right where vector v ends. So we're going to go over 1 and down 2, and this spot right here at 4, 2 is our resultant vector vw. The dashed vectors just show you that we could have started here and gone vector w first and then added to that vector v. So it really doesn't matter. In fact, it's also called the parallelogram rule because this outer quadrilateral here is a parallelogram. So it doesn't matter if we go v plus w or if we go w and then v. What matters is, how far we go and what direction we're going ultimately. So in any event, they all sort of cluster here around 4 and 2. Scalar multiplication is multiplying our vector by a real number or a scalar to get a new vector. And the reason it's called a scalar is because it scales the magnitude or the length of the vector based on what you multiply it by. So for instance, let's say we have a vector v here. If we multiply our vector v by -1, in an earlier slide I said it makes your components their opposite. What happens from a visual perspective when you do that is it flips your vector around. So now where it was, the tail end of it is now where the beginning of it is, and now it's pointing the exact opposite direction. So a bit of a U-turn. If we have vector v here, we can double its length, not change the direction it's going, but double its length rather, by multiplying it by 2. So notice that these two vectors are going the same way. They are parallel because they're pointing in the same direction, but this vector here is twice the length that this vector here, vector v, does. So hence why we call it a scalar. It's going to scale your vector, which actually also multiplies your x component by 2 and your y component by 2. So if you think of it like a right triangle, if we multiply the hypotenuse by 2, we have to multiply the base and the height by 2 as well. So that goes back to similar triangles from geometry. So any real number times our vector, it's essentially gets distributed to each component. So the horizontal or your x component and the vertical or your y component. So vector subtraction, we saw that vector addition followed a parallelogram rule. Vector subtraction does in a way as well. So vector v minus vector w. Well, if we kind of trace out the following path here, we got vector v. Vector w is pointing this way, so vector negative w would be pointing the opposite direction. So we take vector v plus a negative vector w, that's going to end up right here. So we actually start here and end here. So we started where v started, but we're ending at the arrowhead for negative w. If we pick this dashed purple segment up and move it, because remember, we're not changing its length or direction, we can pick this purple segment up and move it so that way its initial point is on w's terminal point and its terminal point is on v's terminal point. So if we could physically move this over here, and we have vector v minus vector w, which we will revisit in the next section when we talk about dot product. So some properties of scalars. Number one, it's associative. So if k and r are real numbers, then we could either multiply k and r together and then multiply that by a vector v, or we can take vector v times r, whatever that is, multiply it by k. So once again, we can associate the parentheses with any two terms. 1 times a vector will give you itself, the vector, so that's your identity property. Negative v is -1 times v, and we saw what happened visually, how it turned the vector around the other direction. K plus r, again, these are real numbers here. We can almost distribute our vector over these scalars, so k times vector v plus r times vector v. We can also, if we have two vectors added together and we multiply that result by a scalar, it's going to give us the exact same answer as if we just distribute our scalar to both vectors. So k times vector v plus k times vector w. K times vector v is 0 if and only if either k is 0 or vector v is 0. So just like in algebra class where two things multiply together to make 0, at least one of them has to be 0, maybe both, but it's either the first or the second. It's either the first or the second, but again, it could be both. So now we're going to look at solving a vector equation. This will be our last example in this video. So we have solved 5 times vector v minus 2 times the expression. Vector v plus the component 1, -2 is going to equal the 0 vector. We want to find the horizontal and vertical components for vector v, or to put it another way, the x and the y coordinates. So the 0 vector is just 0, 0 in this case, since we're only dealing with 2-dimensional vectors. 3-dimensional does exist, and there's quite a lot of that beyond this class in upper level mathematics courses like Calc 3. but we'll deal with 2 dimensions because I'm not that good at drawing in 3 dimensions. So if we replace vector v with x and y, horizontal and vertical components, inside these parentheses here, we have xy plus 1, negative 2. We can add the horizontal components, x plus 1, add the vertical components, y plus negative 2. And we could also distribute our 5 to the x and the y. So we have 5x plus 5y minus 2 times the expression x plus 1 as our horizontal component and y minus 2 as our vertical component. So now if we distribute this 2, we're going to take 2 times x plus 1, 2 times y minus 2. So essentially distribute the 2 to all 4 of the terms. We get 2 times x is 2x plus 2, and then 2y minus 4. And now we have 5x in this horizontal component. We have 2x plus 2 for this horizontal component, 5y for the vertical component, 2y minus 4 for the vertical component. We'll just distribute this subtraction. So we get 5x minus 2x minus 2. 5x minus 2x minus 2 is 3x minus 2. And then 5y minus 2y minus 4 becomes 5y minus 2y plus 4. And 5y minus 2y is 3y. So we have 3x minus 2, comma 3y plus 4 are both going to, those expressions are each going to equal 0. So set each one equal to 0 and solve. We get x is 2/3, y is negative 4/3. So our final answer is the vector with a horizontal component of 2/3 and a vertical component of negative 4/3. And if you plug it into the original problem, on the left-hand side, after you're done doing all the math, you should get zeros back in return, so it should check out. All right, that about does it for this video. In the next video, we'll take a look at finding unit vectors